Now, before we jump into correlation IDs, I want to show you the overall request flow of this application. Because once you understand how a request travels through the system, the purpose of middleware and tracing becomes instantly clear. Let's say a user sends a request to simplify a medical report. That request doesn't magically jump into the business logic. It follows a structured path through multiple layers of the backend. And understanding that path is one of the keys to writing maintainable systems. So where does everything begin? Well, everything begins in the main.py file. This is the entry point of our application. Think of main.py as the control tower. This is where we create the FastAPI application, configure metadata like title and version, register middleware, and include our route modules. So when the server starts, main.py is what assembles the whole backend into a working system. It wires together different moving parts. Once the application is running and a request comes in, the first major step is the middleware layer. Middleware wraps the request lifecycle, so before the request reaches any route, middleware gets a chance to inspect it, modify it, log it, authenticate it, or attach useful context. In our project, the middleware generates or extracts a correlation ID and stores it safely for the lifetime of that request. This means from the very first moment the request enters the system, it already has a tracking identity. We'll see why this is extremely powerful for debugging later. After our middleware, the request moves into the routes layer. This lives inside our API directory and in turn under the routes directory under the API directory. Routes define the actual HTTP endpoints exposed by the backend. For example, post/simplify report is the endpoint the client would call for simplifying a report. When the route receives the request payload and validates it using Pydantic models, it logs the request and then delegates the real work to the service layer. Now, before we move on to the service layer, I want to give you a quick walkthrough about Pydantic models because this is one of the most useful tools in FastAPI and one of the reasons FastAPI feels so clean to work with. At a high level, a Pydantic base model is a Python class used to define the shape, rules, and expected types of data coming into or going out of your application. Think of it like a contract. It tells your backend this is what valid data should look like. For example, in our patient scribe application, when a client wants to simplify a medical report, they might send data like this. Just a dictionary with a patient ID and some report text. Instead of manually checking if these fields patient ID and report text exist, checking whether they are strings, and validating the input ourselves, we can merely define a Pydantic model as such. Now that we have created a clear schema for incoming data, this means that every request must contain a patient ID, which must be a string as we have defined here, a report text which must also be a string, and if the incoming request doesn't match this structure, FastAPI automatically rejects it with a clean validation error. This saves us from writing repetitive validation code. So, what does Pydantic actually give us? Firstly, it gives us validation. If someone sends us a dictionary with an incorrect data type, like this, where a string is required but a Boolean value is present, it would check the data and raise an error because the types don't match what we declared. Second, automatic parsing. If valid data is received, FastAPI converts it into a Python object. So inside our route, instead of manually reading dictionaries, we can do something like payload.patientID and payload.report text. This means that we don't have to manually parse data and it feels cleaner, safer, and easier to maintain. Thirdly, documentation. Because FastAPI understands Pydantic models, it automatically generates beautiful interactive API docs. Your request body schema instantly appears in Swagger UI. That means your model is not just validation code, it also becomes documentation, and it's one source of truth doing multiple jobs. Fourth, maintainability. As your application grows, data contracts become more important. Instead of wondering what a function expects, the base model makes it explicit. Anyone reading the code immediately understands the required structure. Now let's connect this back to our application patient scribe. Our route might look something like this. Router.pose, excuse the AI code prompts or AI, the code that's automatically generated by AI. So our route might look something like this, and this single line tells us a lot. This endpoint expects a request body shaped like report request, where report request is our Pydantic model. So before our route logic even runs, FastAPI and Pydantic have already validated the incoming data. Now if you've worked with backends like Flask or framework like Django, you would understand how incredibly powerful this is. To summarize, think of Pydantic models like airport check-in counters. Before passengers board the plane, documents are verified, baggage is checked, and invalid entries are stopped early. That way, the flight system itself runs smoothly. Similarly, Pydantic ensures only valid data enters your application logic. Now, let's go back to routes and report services. We have clearly defined separate modules, and not just us. Every senior developer and every developer who follows good practices separates concerns like routes and APIs into different routes and services into different modules. This is an important design principle. Routes should remain thin. They should coordinate requests and not contain heavy business logic. Think of routes as receptionists and not surgeons. Then the request enters the service layer. Notice how we have called the simplify report service from our simplify report route. The flow of control would then be passed on to the report service module where the simplify report function exists. This service is responsible for processing the report text that's passed in through the request sent by the user. Today, I've just included a placeholder logic, but in the future, we're going to call an LLM, retrieve patient context, summarize findings, generate structured outputs, and interact with multiple downstream systems. That's the whole reason why we isolate services. Because business logic evolves constantly and we want it separated from HTTP concerns. So if we visualize the flow, it's going to look like this. Main.py receives the application traffic. The middleware runs first and checks the requests. The route handles the endpoint. The service performs the business logic, and the response returns back through middleware. After which the client receives the results on the front end. This layered structure gives us major benefits. It keeps responsibilities clean, it makes code easier to test, and helps teams scale development. It also allows production features like correlation IDs, logging, and authentication to plug in elegantly. Now that you understand how a request moves through the system, we can finally talk about why correlation IDs are such a game changer in modern backend applications. Now we have finally moved on to one of the more interesting aspects of this playlist's introduction, correlation IDs and logging. Now, what is a correlation ID? Well, I didn't know what a correlation ID until I wanted to find out more about production grade practices in terms of configuration and logging. So a correlation ID is just a unique identifier attached to a request. Think of it like a tracking number. When a request comes into your system, we assign it an identifier, and every log generated while processing that request includes the same identifier request. You would be wondering what is going on and how to even track the request that's being problematic and troubleshoot it. So why do correlation IDs matter even more with FastAPI? because FastAPI is asynchronous and things get tricky when and for asynchronous requests because multiple requests are being processed at the same time in the same process. So logs from different requests get mixed together constantly. Now, here's the beautiful part. Throughout this journey from middleware to route to service, every log line can automatically include the same correlation ID. So your logs may look like this. That means even if 50 users or 50 million users hit your API at the same time, you can still trace one request cleanly from start to finish. Without correlation ID, your logs become almost impossible to debug. With correlation IDs, you can reconstruct the story of a single request from start to finish. Now, you might think, or even I thought, why let's just store the correlation ID in a global variable. That's a rookie mistake because that's where things break. Let's say request A sets the ID to A123. Before it finishes, request B comes in and sets the ID to B456. Now, when request A continues, it logs using B456 instead of its actual identifier, which is A123. And this is the problem that context variables solve. A context variable is created once, but each request gets its own value. So even if multiple requests are running at the same time, they do not overwrite each other. Think of it like a hotel reception desk. Each guest gets their own room key even though the same desk is used. So request A gets A123, request B gets B456, and they stay isolated. This gives us request level storage in asynchronous systems. Now, how do we even implement correlation IDs and context variables? Let me show you real quick. We implement it through our middleware. Just to recap, a middleware is where everything comes together for requests. A middleware is simply code that runs before and after each request. So instead of going directly to your route, a request first passes through middleware. Think of it like airport security. Every passenger goes through TSA before reaching their gate. Similarly, every request goes through the middleware before reaching the actual API route and then the services in turn. In our patient scribe application, a single request might trigger parsing, embedding generation, vector search, and an LLM call. If something fails in the chain, we need to trace what happened. Instead of modifying every function, we use middleware to handle cross-cutting concerns like correlation IDs. Now, let's take a look at what our middleware actually does. When we have defined helper functions get correlation ID and set correlation ID, which these two do nothing more than retrieving a correlation ID from a context variable and setting a correlation ID in a context variable. As for the code for our actual middleware function, when a request comes in, it checks if there is already a correlation ID in the headers, and you would want to look right here. If there isn't a correlation ID in the header, it generates a new one using UUID. Then it stores that ID in a context variable. At this point, every part of the application can access it. Then the request continues through the system. And finally, when the response is ready, the middleware attaches the same correlation ID to the response headers. So the entire life cycle is wrapped this way. The request comes in, the middleware code is executed, the application logic is executed, the middleware runs again on the way out, and the response goes out. Now, a small but important detail. In our middleware class, we have defined a method called dispatch. This is not arbitrary or random. This is deliberately called dispatch because we are inheriting from a base middleware class. Let me show you where it is right here. What we are doing here is overriding. We are inheriting from a base middleware class, and that class expects a method called dispatch. So we are overriding that method. If we had renamed it FastAPI would never call our middleware logic. So that's a quick walkthrough on correlation IDs and context variables. And in the next video, we'll see how we shift from native logging to pro level logging using Loguru. Cheers, guys.